Hey there, it's Mrs. Vara. I'm going to do an example for the next section of the 4-8 notes. So this will be the second video for the 4-8 notes. At the top, this is page 24. At the top of the page, we just have a reminder of how you find direction. So we use the angle to find direction, and we use the tangent. And then the y over x, this will be the y component of the vector, and this will be the x component of the vector. And magnitude can also be known as speed, which in a lot of these examples, it will, hang on, I'm going to zoom this in a little, it will be speed. So the first one says a plane leaves an airport heading 20 degrees south at 600 miles per hour. So this is your magnitude. 600 miles per hour. A wind is blowing in the direction of 40 degrees north at a speed of 25 miles per hour. So that is your magnitude. So what we have is a plane heading in one direction and the wind pushing it in an opposite direction. So let's draw a picture of this to kind of get it set up. So you want to draw basically a north, east, south, west. So kind of like a coordinate grid, but you're going to want those directions on there because as you can see, they're using this south of east and north of east. So never eat shredded wheat or never eat soggy waffles, whatever you use there. Now let's see if we can draw a vector that represents the plane. So a plane is leaving an airport heading 20 degrees south of east. So here's east. South of east would be down here in what we call quadrant 4. So this vector will represent our plane. Okay, so this angle here is 20 degrees. So I'm writing 20 degrees now, but when we put it in our equations, we're going to use negative 20 because we measure angles that go down here as negative angles. And the length of this vector, which magnitude is the length, is 600. Okay, so this is the direction the plane is setting out in. Now a wind is blowing in the direction 40 degrees north, so that would be toward north of east. So here's east. If you're north of east, you're up here. And I'm going to make this one shorter because the magnitude of this vector is 25 and this angle is 40. So what's happening is the plane is trying to blow in this direction. There's a wind coming from this direction and it's going to change, and its actual direction will be what we call our new vector or our new position vector. So what we're going to do is we're going to add these vectors. So if you picture adding vectors is when we do that tip to tail. So we would think about translating this vector right down here. So the tip of this vector lines up with the tail of that vector. And then the new position would be this vector. So this is the new position vector. Okay, now what the question is asking, find the actual speed and direction of the plane. So the actual, so I guess I could have called this actual, is what I'm calling the new. This is the plane, this is the direction and the speed that the plane is heading in right now, but the wind is pushing on it, and this is its actual vector. So this will provide the actual speed and magnitude. So we need to write this vector. So the way we do that is we're going to write a vector that represents the plane, which I'm going to call vector P. And then we're going to write a vector that represents the wind, which I'm going to call vector W. And then we're going to add those two vectors together, and this will be our new vector. And then we're going to find the speed and the position of this new vector. Okay, so let's write our wind vector first. So we know the magnitude and we know the angle. So remember, it'll be magnitude, which is 25. So the x component will be cosine of 40 degrees because that's our angle. And the y component will be magnitude times sine of 40 degrees. Now, if you're putting this in your calculator, which you probably will because we're going to get some decimals, make sure you are in degree mode, not radian. So if you put all that in your calculator, you're going to get 19.151 for your x component of the wind vector and 16.070 for the y component of the wind vector. Okay, now we want to write a vector that represents the plane. So that's going to be 600 cosine of negative 20 and 600 sine of negative 20. So x is always cosine and y is always sine. And so 600, let me fix that, sine of negative 20. So that's your plane vector. And then you want to put all that in your calculator and you're going to get 563.815. That's the x component, and the y component will be negative 205.212. So that is your plane vector. Okay, now we want the actual or the new position. So we have a vector for the plane, we have a vector for the wind, now we're going to add them together. So when we add vectors, we just add the x component and the y component. So I'm going to call this new. I'm going to call this vector n for the new position or the actual position. So all I'm doing in this step is adding 19.151 plus 563.815, adding the x component and adding the y component. When you do that, you get 582.966 for the x component of the new position vector and negative 189.142. Okay, so that is our new vector. We've defined this vector right here. Now we want to find the magnitude of this vector, which will give us the speed, because they asked us for the speed and the direction. So speed is going to be magnitude of vector n, which is going to be the square root of 582.966 squared plus negative 189.142 squared. Again, you're going to put all that in your calculator, and we want to say approximately equals because we're chopping off some decimal points here. That's going to be 612.882, and that's miles per hour. This is a story problem, so you do need units. Story problem requires a story answer. So in this case, it's actually speeding the plane up a little bit. The plane was going 612, and the wind is increasing the speed slightly, so it's pushing the plane a little bit. It's going a little faster. It's also changing direction. So direction comes from your angle. So we want to find the angle. So to find the angle, what we're really doing is we're really saying the tan of an angle equals y over x. But we want the angle. We have the y component of our vector. We have the x component of our vector. So we're just going to go right to tan inverse. So direction is defined by the angle. So we're going to say theta equals tan inverse of y over x. So the y component of your vector, negative 189.142, divided by the x component of your vector, 582.966. So y over x. Now again, use your calculator. Make sure you do tan inverse. And what you should get is theta equals negative 17.975 degrees. This is why a picture is pretty important, because that makes sense. This is where we drew our new vector, and the plane was originally at minus 20. Our picture shows the angle should be a little bit less, and it is. It's about at negative 18. The other thing you want to check is sometimes when you do these problems, it will give you an angle in the quadrant 180 degrees across from it. So you need the picture, because if it gave me an angle over here in quadrant 2, I would have to add 180 to it, so it makes sense for our problem. So make sure these numbers you're getting are making sense. Now, this is the angle, but in these problems, we don't want to write just the angle. We wanted to describe it like they're describing it. So this would be south of east. So the direction would be, and I'm going to say approximately, I'm going to round that up to 18 degrees, 18 degrees south of east. So we want to give our answer using these bearings, which is how they gave it in the original question. I'm going to actually do this one in class, so we're going through one kind of in person. This is the one that I want you to try. So I'm going to start you off on it by just helping you draw the picture. And then give it a try. I know we only did one example, but still give it a try. We will do another one in class, so if this one doesn't go well, that's fine. We will go over another one, and then hopefully the next one will go better. Okay, so a river flows directly north. So this is directly north. So this is going to kind of be our river, which doesn't show up very well here. So that's our river. Directly north means this angle is 90 degrees. And it has a magnitude of 8, so the length of this vector is 8. Then it says a ferry boat leaves the west side of the river. Well, my river just kind of is really skinny, so a ferry boat leaves the west side of the river. If I had actually drawn a river, it's saying it would leave this side. And heads 25 degrees north of east. So here's east. If I'm north of east, I'm up here. And it has a speed of 20, so I'm going to make this one a little longer. So that vector represents the boat, and this is 20. Oh, my lead is doing funky things on me here. 25 degrees. So this is the boat. Okay? So that is what is happening. So if you wanted to kind of picture what's happening here, we have the river and we have the boat. So if we do, I'm going to kind of sketch this down here. If we have the boat and then the river, which has a current and is pushing on it. So this is the river, this is the boat. This would be our actual or our new vector, our new position vector. Okay, so this is the one where we want to write a vector that represents this and then find the speed and direction of that vector. I think these answers are in the slide, but I'll go ahead and give these to you if you're trying this on your own. You should get a speed of approximately 24 0.478 miles per hour, and you should get a direction of 42.22 degrees north of east. So give this one a try, practice setting it up, and we will go over one more in class.